Alright guys, in this video we're going to be talking about concurrent lines, medians, and altitudes as it says. We've already talked about some of the different things, and we're going to introduce a couple of new topics. But concurrent lines, let's think about what concurrent lines are. When three or more lines intersect in one point, so three or more lines have to intersect in one point, they are what we call concurrent. And the point at which they intersect is the point of concurrency, and we're going to have four such sets of lines for triangles. So we're talking about four sets of concurrent lines. Now, the first set deals with perpendicular bisectors. Now, think about what a perpendicular line is in a bisector. A perpendicular bisector. The point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter of the triangle. And if we could draw a perpendicular bisector, so you know what, I started that one wrong. Let's back up and let's erase that one. I was looking at that totally wrong. I went from the wrong point. What is a perpendicular bisector? Well, a perpendicular bisector is a line that is perpendicular to a side, and it bisects that line. So here we have, notice that line, it can come off, and it is perpendicular, using the wrong, and it bisects it, right? So we have three of those alike in all of our different so like that. That looks a little off, doesn't it? I don't think that bisects. Let's move that over. That's probably about it, right? And if we really look at this one, I don't think that is. And the last one. Oh, didn't say, hey, it's perpendicular. And it bisects. And then we have the third perpendicular bisector. Well, it'll go right up through here. Notice that all three of those lines do intersect, perpendicular bisectors, and they intersect at a point. Now, that point is very special to us. That point is what we call the circumcenter of the triangle. What does that mean? That means that we should be able to take a circle and draw a circle to where all of these vertices are on the edge of the circle, and this would be our center. I know that's a horrible circle. I apologize for that. Here's one. Maybe I can get that pretty close. So that's what we would be looking at there. We can draw the center of that circle. So that is the perpendicular bisector. Now let's look at the second one. We have what is called the end center. I'm sorry, I was losing what I was doing. But the end center is where we have the point of concurrency of angle bisectors. So instead of looking at perpendicular bisectors, we can now look at angle bisectors. And if I draw a line and I bisect that angle there, so that means what? That this side is equal to this side, or this angle, and we draw this angle bisector to where this angle is congruent to this angle, and we draw this perpendicular bisector where this angle is congruent to this angle. So that gives us another point of concurrency, and this point of concurrency is what we call the end center. Here, what this means is we can draw a circle inside of the triangle to where it is touching all the different sides, is the way that that should work. Now we know that this is not to scale, but that is what that should look like and should be. And that is the end center. So let's look at the third set. Here we have to introduce a new topic, first of all, and we're talking about an altitude. What is an altitude? Think about altitudes of planes. If we're talking about the altitude, what is its distance right from the ground? Well, the altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. So if I'm looking at this line and I draw a line that is just perpendicular, there's the altitude. Sometimes the altitude is the segment or a side itself. Also, sometimes the altitude can be drawn outside. And so there we have the altitudes. Now, altitudes are sometimes difficult to draw when all three of them are intersecting. But in this case, the altitude, the line of concurrency, or the line containing all those, are concurrent at what we call the orthocenter. Orthocenter being, if I were to draw the altitudes, they would intersect, and that is the orthocenter. We don't really deal a whole lot with orthocenters. The last and final one of our four is when we have a median. Now, a median, think about the median in a highway. It's in the middle, correct? Well, that's just what we have for here. We have a line segment that goes through the midpoint. That's all we know, is it's there at the midpoint and it goes to the other vertex. So if we draw all three of our medians, all we know is that each median goes through a vertex and to the midpoint of the opposite side. So we know that those segments are equal thus. And that is what a median is. And the median, where they intersect, is called a centroid. So in a triangle, the point of concurrency of the median is the centroid. Now, here the centroid is very important to us. If we have the medians drawn, and let me draw those real quick. So here we have all the medians drawn, and in this we can see that we have the different labels as well. Now, the point in the center, or our centroid, we're going to call point H. This is point H, is our centroid. Now, why is this so important? Because the medians of a triangle are concurrent at a point that is 2/3 of the distance from each vertex to the midpoint. Think about what that says. 2/3 the distance from each vertex to the midpoint. So what that means is if I'm looking at AE, I'm looking at this segment right here. That means that the segment from the vertex to the centroid is 2/3, so AH is 2/3 of the whole segment length, AE. So if AH is 2/3, then we can conclude that HE is 1/3. HE is 1/3 of AE. So how do we put this in retrospect? What if we're told that AE is equal to 12 units? Find the length of AH and HE. So we're looking at 2/3 of the length. So if AE is 12, the whole thing is 12 units, then AH is going to be 2/3 of that. So 2/3 of 12 is AH. Remember how we multiply fractions? So 2 times 12, 24 divided by 3 is 8. So AH is equal to 8. And HE, if we want to follow the formula, would be 1/3 of 12, which is 1 times 12 over divided by 3 would be 4. Now, does that make sense? 8 plus 4 gives us 12. And that is how we can use the centroid. Very, very nicely done. So let's look at another problem. So in this next problem, we are very, very similar. Kept the lettering the same way. Same situation, but in this case, AE is equal to 15. We want to find AH. Now remember, that from the vertex to the centroid is 2/3 of the length of the whole segment. So AH is 2/3 of the whole. So AH, I guess it's hard to write with a highlighter, AH is 2/3 of AE. And AE is 15 in this problem. So multiplying, 2 times 15 is 30. 30 divided by 3 gives us 10. So AH is 10 units long. Now, we can just do simple math. If AE is 15 and AH is 10, then we know that HE is 5. But we may not always be given that. Let's look at the same problem but different. Here, let's look at CD, looking at that segment of CD. Now, CD is equal to 18. We want to find HD. So we have to determine HD. Well, HD is this segment here. Is it from the vertex to the centroid? No, it is not. HD is from the centroid to the opposite side. So that means that this side over here is my 2/3 segment. If this is 2/3, then this is my 1/3 segment. So therefore, in order to find HD, HD is going to be 1/3 of 18. Now, since it's 1 times 18 divided by 3, because we're multiplying straight across. So 18 divided by 3 gives us 6. So HD is 6 units. And if HD is 6, then if we did our math, CH would be 12. 12 plus 6 gives us 18. Let's work backwards in a problem like this. Let's say that we have the next example. Still using the same lettering and so forth. Whoops, a little bit out of screen, isn't it? What if we're not given the whole segment? What if, let's do two problems. What if we're told that FH is a certain length, and we're also told that AH is a certain length? So, given the fact AH equals 6, we want to find AE. So think about what we know. AH is from the centroid, from the vertex to the centroid. So AH is 2/3 of AE. Plug in what we know. Well, AH is 6. We're solving. Have to complete our math here. Now, how do we get rid of the fraction? Well, we can multiply by the reciprocal, correct? So if we multiply by 3/2 over here, it'll cancel. So then I'd have to multiply by 3/2 over here. So 3 times 6 is 18. 18 divided by 2 gives us 9. Therefore, AE is equal to 9 units. And for our last problem, FH. FH is equal to, let's say 3. FH is 3. Well, if FH equals 3, we want to find FB. Now notice that BH is my 2/3 segment, right? BH is the 2/3. So if BH is the 2/3, that means that FH is 1/3 of FB. 1/3 of FB. So 3 equals 1/3 of FB. How do I get rid of 1/3? Simply by multiplying by 3. Multiplying by 3 cancels, and 3 times 3 gives me 9. So therefore, FB equals 9 units, because 3 times 3 gives us 9. So if this segment is 3, the whole segment is 9, so that means this is 6. We just wanted to plug that in. So hopefully that this helps. out, and we understand that from the vertex to the centroid is 2/3 of the length of the whole median. 2/3 of the length of the whole median. So take care of yourself.